Click.
Right click. Oh, I forgot to get my mouse. Hold on. Right
Yeah,
click.
yeah.
Okay, yep, yep.
Presenter view. Show
Oh, it's
presenter
okay.
view.
Okay, great.
You are able to see your notes.
I see my notes, but I don't see myself.
No, you will see when you
Then
share the
for that
screen.
you have to
No,
upload it.
when you share your screen, no, you will your video become a small size. You just
Okay,
click Alt Tab. Not an issue. We are able to see you and your presentation. Not an issue.
okay,
No, no,
Exactly
she's.
5 minutes will start. 6 5.
okay.
But if you have to upload, then only she will be able to see herself. No?
Oh yeah, that's
Are
true.
you able to
No,
see
sir.
your?
See, no, sir. The small screen is minimized, sir. Not issue, sir.
No, whether she is
Yeah,
able
but I
to see
think I
that.
have to upload, right?
No, upload based on
No,
your
no. Are you
internet.
able to see yourself? Are you able to see yourself
I
on
was
the
not
same
able to.
screen?
Yeah,
No.
I was not able to
You are
see
able to see
myself.
the slide. You are
No,
able to see only PowerPoint screen.
I can
That's all.
only see my PowerPoint screen.
No.
So I think I
Yeah.
have to upload, right? So I forgot how to
Yeah.
do
If
that
you
again.
upload, then only yeah.
So how
Because
do
your
I up?
Upload that.
image size is higher, madam. If you upload, it will take a time. That's why.
Oh, okay. Well, we
Not
can
a
Let
issue.
just do.
let her try.
Yeah.
Let her try now.
That's fine. Can just I can do it without.
Hello, I am Professor Shashank, Principal of MIDAS. Welcome to Architecture and MIDAS. Architecture is a creative field that combines imagination and practical knowledge. Architecture is also a field that deals with designing of shelters, one of the three basic necessities of human beings apart from food and clothing. For any architectural education institute, three things are essential. First one is the infrastructure, second one is the mentors and the faculty, and the third one is the environment in which this teaching learning process takes place.
Prior to coming here as the Dean of MIDAS, I had been to many other places in the capacity of teaching as well as in the capacity of professional practice. I'm a person who truly believe in nurturing the education within. So my message to the students and parents and the faculty of MIDAS is that everybody is bestowed and gifted with their own unique talents. Somebody has to nurture it. Somebody has to help you identify your strengths and then work on it to become successful and grateful. So MIDAS is a place where you can come, get identified. You can find out who you are, what you are. And this is the place which is bestowed with such faculties and the facilities which helps and nurtures the students to come, find out, identify and conquer the world.
I will like to say that those who wish to explore their interest and satisfy the passion, MIDAS is the best place.
of MIDAS. I am Principal Professor Shashank. I also thank Dr. Sigrid Adriaenssens for accepting my invitation to deliver her lecture on her topic of research topic especially, and for our students as well as participants. Really, it is a great day for us today because we are privileged to have you here from the top ranking university. And before you begin your session, I would like to uh, introduce yourself to the audience without taking much time. A brief introduction of Dr. Adriaenssens. Dr. Adriaenssens' research focuses on lightweight surface systems and how they can be optimized and realized to interact with extreme structural or environmental loading. This includes research on flexible and rigid shells and plates, submerged flexible membranes and nets, and metamaterials with applications for a resilient urban environment. The application ranges from adaptive building shading devices to large-scale inflatable storm surge barriers, and are sometimes inspired by systems that evolved in biology, art, or architecture. Dr. Sigrid leads the form finding lab at Princeton University, USA. Before joining academia, she was structural designer for Jane Warnick Associates, London, UK, and Ney and Partners, Belgium. She obtained her PhD from Lightweight Structures Center at Bath University, UK. In 2018, she received the American Society of Civil Engineers George Winton Award. She co-chairs International Association of Shells and Spatial Structures Working Group 5 and the ASCE Aesthetics in Design Committee, and co-edits the International Journal of Spatial Structures. Now I welcome our esteemed speaker of the day, Dr. Sigrid Adriaenssens, to this virtual session and request her to take up the session on shell structure for our audience. Thank you very much. It's all yours now.
Good evening, everybody. Can you?
Yes, ma'am. We can hear you. We can't hear you right now, ma'am.
Ma'am, kindly unmute yourself. No, you are muted. Okay.
Can you?
Yeah, you're muted, ma'am.
Can you hear me now?
Yes, ma'am. We can.
Yeah. All right. Okay. So maybe before I start, I just want to say that I think when I was about your age, I actually spent 6 months in India. I did an internship in India, and I remember I was so this was actually when I was a student, and you know, I went to visit the Taj Mahal, and I know that in India actually there are a lot of shell structures still being built today. So I just want to say I have very great admiration for your country, and I have very fond memories. I was there when I was very young, and when all this was time before the internet, when all these impressions made a very big impact on it. So I just want to say that, I mean, that, you know, like when I was your age, I had the great privilege of spending, you know, quite a lot of time in your country. So I'm gonna start. Actually, this is not really my presentation. My first slide. Wait, let me set this up properly. So I'm gonna go to slideshow, and then I'm gonna
make it full screen
from beginning.
Hold on, from the beginning. Okay, can you see this slide?
Full screen.
Not yes, ma'am. We can.
Not yet full screen.
Okay, so just for you to maybe have a little bit an idea of where I am at the moment. So for me, it's morning time. I've just woken up with my family, and we are on the east coast of the United States. Princeton is a town very close to New York and Philadelphia, and it is also the setting for a lot of movies. And I don't know if any of you are big movie fans, but you know, it featured in the top left. It's an image of A Beautiful Mind about the mathematician Nash, who was spent considerable time of his life in Princeton. In the middle, on the right-hand side, you recognize Batman. So Batman supposedly is an alum from Princeton University. On the left-hand side in the middle, you see the talented Mr. Ripley. And you can see the logo on his blazer. So he pretended he didn't actually go to Princeton. He pretended he went to Princeton. And then the bottom one is another picture of a campus. And that is from the Transformers. That's the most recent film that was. So if you ever come to the United States, the East Coast, you definitely have to visit Princeton and come and visit me. And you will see all these amazing places. Okay, I think that's enough introduction. I'm going to start talking about my research that I do with all my students. So about 10 years ago, I moved. I'm actually originally from Belgium. I moved with my family to the United States, to New Jersey. And, besides doing work, we sometimes go to the seashore. And then we see things like this. So these are bridges that I see, on the highway when we go to the seashore. But what I notice is, mostly for me at least, that these bridges are very massive, right? The profile of the bridge is constant along its length. And that always surprises me, because the construction industry is one of the most resource and most wasteful, at least innovative sectors in the world compared to all the other industry sectors. Because I know that, if you design a beam that is more on one support, so basically this bridge is like a beam on 3 supports, you should, this is my sketch, design it like this, right? That is really the ideal form to take all the forces that will go into that bridge. And you see, you would actually save a lot of material. So if you model the bridge according to the forces that are within it, you can save a lot of material. And of course, if you save a lot of material, you can also have a smaller carbon footprint. And then when we get to the beach, this is kind of what the East Coast looked like, right? So, I remember the beaches in India, it looks in some places similar. So we have a lot of people. This is, of course, today not possible, although people are still going to the beach. You're not really supposed to be doing this today. But what we see is that there's a lot of, this is actually a picture of Rockaway Peninsula near New York City. And you see a lot of people on the beaches, a lot of accommodation. And we all know that the urban populations are growing. So, but also in 2012, the East Coast gets affected by tropical storms. Actually, we just had one last week, as you remember, or I don't know if you know, but actually this lecture was planned for last week. But last week we had a tropical storm and our electricity and internet went out for a couple of days. In 2012, we had also another tropical storm, Hurricane Sandy, which was worse than the storm we had last week. But it caused a lot of damage, that storm. And here you see some images of what happened to the houses that were constructed next to the beach. These are images from like a movie. It looks like as if they're from a movie, but this is real. And so there were enormous economic and social losses when that storm hit. And what has been the response after Hurricane Sandy? Beach communities were looking to repair their houses, but also build some stuff to keep the storm surges out. And what they were doing is really, they were rebuilding the boardwalk as it was before. So basically, they're not really upgrading their coastal defense system. They are just rebuilding the stuff that was before. And as you can imagine, that's really a disaster to be waiting to be happening again, because again, so many years later, 2020, we have another big storm, right? And we know that due to climate change, these storms are going to become more intense and more frequent. Or another way, so some people just rebuild the boardwalk, other more affluent communities like this one here in Brick, New Jersey, they build a seawall. So the idea here is, if we put a lot of stones, or in some cases, if we put a lot of concrete, if we cast a lot of concrete, that will keep out very strong and destructive forces of the storm surge. And this, of course, has disadvantages because, these kinds of walls, well, first of all, they prevent you from going on the beach. Also, there can be no migrations from animals that are in the water onto the land. Also, if you have real estate here, your value will go down. So in my opinion, building these seawalls is permanent, rigid seawalls is not the solution to this problem. So what kind of questions do I answer in my research? First of all, I look at what is the relationship between form and efficiency in structures, and also how can we develop algorithms and methodologies so that we can go from this massive tradition where we use a lot of stone and a lot of concrete to a lightweight, forced modeled framework, and how can our quality of life then become better? And so really my research kind of intersects statics, dynamics, solid mechanics, form finding and optimization, and architectural and environmental science. And in this quest, I'm not really the first one to think about using forms to carry forces rather than mass. And what I've drawn here is a graph with, on the x-axis you have time, and on the y-axis you have weight in terms of kilonewtons per meter squared. Of course, on the top left, we have the pyramids, right? Okay, that's a form, but that's a solid form, so it's extremely very, very heavy. And as we go down, we see, for example, number 4 is the Hagia Sophia in Istanbul. Number 8, those are the Gothic vaults. And as we go down, if we go into the 21st century, there are a number of points. We see that, and remember, this is a logarithmic scale, right? So on the y-axis, we go from 0.11 to 10 to 100 to 1,000. That's a logarithmic scale. So what we are seeing is that a lot of very iconic structures, and I could have put the Taj Mahal there as well. We see that by using a specific form, you can actually build lighter and lighter, and in doing that, you can reduce your construction cost, and you can also reduce the amount of natural resources that you need to construct that form. And I put a little rectangle there around 21st century, because, and what you see here now on the right-hand side is a close-up of that. Those are all, that's a close-up of those points, right? And the structures that I have worked on are structure number 14, and I will talk about that one. And my students have been doing research on structures number 15, so the arch bridge 16 and 17. And you see that actually some of these structures, especially 16 and 17, they start being very lightweight. They are much lighter than a wind. So they have to actually be designed really, really well, so that when you get wind upwards loading, when you get wind suction, that they don't get blown away. Okay, so I am not really the first one to use forms, right? I'm going to talk a little bit about Antonio Gaudí. So he was a Catalan architect in the 19th century, and you see him here. He's the one with the white beard, and he used something that Robert Hooke, and you might know Robert Hooke because he has made a lot of inventions, or he has discovered a lot of things, like, for example, what's the relationship between displacement and force. That is stiffness. But he was in the Royal Society in London, where they didn't have the internet or anything like this, so they would hang out there and ask each other difficult questions. And the question that was asked was, what is the ideal shape for an arch? And he answered that question, but he answered it first in a book, and he didn't answer it in a normal way. He answered it in an anagram, and you see it on the left-hand side. You see all these letters here at the bottom, A, B, C, C, D. Basically, an anagram is an answer where you put all the letters, but you put them in the alphabetical order. So it's impossible to really find out what the answer is for somebody who's reading this, right? But so when Robert Hooke passed away, the executioner of his will revealed what the answer was to the question, what is the ideal shape of an arch? And in Latin, the anagram said, ut pendet continuum flexile, sic stabit continuum rigidum inversum. That means as hangs the flexible line, so with inverted will stand the rigid arch. So basically what that means is if you have a flexible line like a chain and you let it hang under self-weight, it will take on a specific shape. If you were to somehow magically fix that shape so it can't deform anywhere and turn it upside down, that would be the ideal shape for an arch. So what you see here on the left-hand side at the bottom, you see a chain hanging down. And if you mirror image that, you end up with the top chain, which is really the shape of an arch under self-weight. And so, for example, we see that in St. Paul's cupola, which is a religious building in London, you see that indeed, you see here the cross-section of that cupola, and we see indeed that the thrust line or the line of the forces does indeed fall within that cupola. So this is really a method, right? So basically, you can use hanging chains to determine shapes for arches. And the first person to really use this from an architectural perspective to define forms was Antonio Gaudí. And that's why I'm talking about him. What you see here on the right-hand side is a 19th century corridor in a monastery. And you see these are very unusual shaped arches. At that time, when people built arches, they either built basket handle arches or circular arches, but not this shape. This shape, again, is a hanging chain model. So what we saw was a two-dimensional model to define an arch, but of course you can also translate this into 3D dimension, in 3D. Instead of making a 2D hanging chain model, you can make a 3D hanging chain model. And again, Antonio Gaudí used this to define the shape for a chapel. So what you see here on the left-hand side is a sketch for a chapel in Spain. It is a sketch. It was actually never built because the First World War broke out, and there was no money anymore to build this. But what you see here on the right-hand side is the hanging chain model. You have to, of course, turn your head 180 degrees because if you're looking at it straight, gravity is going up. You see all these little sandbags, they're pointing upwards, right? Because gravity is going up. So actually he built it upside down, right? And you also see the white. The white is paper or fabric that he put on the hanging chain model so that he could make the sketch on the left-hand side. And as I mentioned before, construction of this chapel started, but the First World War broke out and there was no money anymore to finish the project. But the crypt of this chapel was built, and that is what you see here on this slide here. So basically what you see here is, you see a crypt. It's made out of masonry and stone. Masonry and stone are materials that are only good in compression, not in tension. And so you see the columns have a kind of weird shape, but these are all hanging chain forms or force modeled forms. So basically the architecture takes the form, it follows the forces that are in that structure. You ever have the opportunity to, or maybe you've already been there, go to Barcelona in Spain, that is where you can find this amazing structure. So my hypothesis is that these kind of techniques, that we can adapt them today so that we can make very large span and material efficient contemporary shells. And I'm going to show a project that I worked on when I worked in industry for Ney and Partners. So now we are in the Netherlands, in Amsterdam. This is a picture of the Dutch Marine Museum. This is a 17th century building. It was a gunpowder warehouse. So you might know that the Dutch at that time were a very very influential seafaring nation. And they would stop at this building to stop up on gunpowder. Afterwards, this building became a prison. And after that, it became a museum. So now it is a museum where they show all the sciences that were developed in the 17th century. So, for example, they have a lot of models of boats there. They have maps there because Dutch really developed map making, so they could explore the world, and also printing. What you can also see, so basically, let me go back to this picture. So when in 2004, this museum was being renovated and the architects wanted So this is actually, you see one facade, but there's actually 4 facades like this. So basically, this is like a quadrant with an open courtyard in the middle. And the architects wanted a roof over the courtyard. So they wrote out a competition to develop a roof over the courtyard. What we did is we went inside the museum and found this map. This is a map from the 17th or 16th century that showed what the Dutch thought the world looked like. And well, besides seeing the very Eurocentric view of what the Earth looked like, you also see that there's a geometric pattern on this. So basically, you have these points here, and they're called windrows. There are 16 of them, and there's a central one. And the Dutch thought that those were the points from which the wind was radiating. And so, the major wind, they thought the major wind directions were along these lines. And so they would use this a little bit like a GPS map to kind of sail around the world. Anyway, we thought that would be an interesting pattern to maybe use for our courtyard roof. The competition called for a very transparent roof. So we're looking for a glass roof that would be supported by a steel grid. And we thought that maybe this mesh could be used for the steel grid. So what you see here on the top is that steel or that grid that we saw on the map extracted. And basically what we did, as you know, so the span of this system is about, in SIU, it's 30 meters, which is about 90 feet. That is the span of one side. And as you probably already know by now, you cannot really span such a large spans with a beam system, because then your beams get very big. So we wanted to develop a curved form inspired by Antonio Gaudí. So what we did is we didn't build a physical hanging chain model like him, but we used numerical models to generate a hanging form. And that's what you see here in the blue below. Again, as you know, this hanging form, once you fix it and you turn it upside down, you end up with a compression form and you end up with a cupola. So we ended winning the competition, and the roof was built. You see it here from a bird's eye. This is an interior view. So again, you recognize the map. This is when you lie on your back, and maybe now you can totally see the map in it. And the other really nice thing we did is that at the nodes of all these beams, we inserted LEDs. So at night, it looks like this. And the idea is really that it makes you remember or the kind of seafaring experience that the Dutch had in the 17th century. So why do we want to do form finding? And well, because, and I'm going to show you this now with numbers. So at the middle column here, this is the bird's nest, or the national stadium that was built in Beijing for the Olympic Stadium. And on the bottom is a much less known stadium on which I worked. It's a soccer stadium, but it also has a grid roof. Now, if you compare these two systems in terms of meters squares, you can't really compare. The one is much larger than the other one. If you compare in kilograms, tons of steel that was used, you know, again, we cannot compare because they're much bigger. If we look at the number of trees that were used, again, we cannot compare because it's much bigger. But if we look at kilogram CO2 emissions per meter squared, so now we are really comparing units per unit. We see that the stadium on the bottom one, the RSCA stadium, uses or production of its steel will produce about 1/3 of that of the bird's nest. So basically, the bottom one is a third, is 60% more efficient in its steel usage than the top one. And of course, I'm not saying that they compare in terms of aesthetics, because there's a lot of aesthetic steel in here, but it does make you think about how we use resources. And the reason for this is what you see here is you see two columns. On the left hand, you see a circular arch. Imagine if you are to design a covering over a train station. If you don't know about form finding, maybe you would give that arch a circular shape like this one here. Or after this lecture, maybe you would take a form find shape, which is this shape here. When you load that shape with its self weight, so just the weight of the arch itself, for the circular arch, because a circular arch is not really a circle or a semicircle is not really the shape that the forces would like to follow. So there will be bending moments, and that's what you see in the top left diagram. There are a lot large bending moments, and of course in the middle you see there's also axial forces. So if you have a span of 30 meters and a height of 7 meters, you would use 13 kilonewtons of self-weight for the arch. However, that is if you're using a circular arch. However, if you're using a form-find arch like this one here, and again, you're analyzing it under self-weight, you would only use 3 kilonewtons. And that is, of course, because there are no bending moments occurring in this shape here. So basically, if you use a form-find arch, you only use, let's say, 1/4 of the weight of the circular arch. So this would be a much lighter arch, which visually will be much more interesting because it will be very, it will be very delicate and very beautiful to look at because it's a very fine line. And also it would cost a lot less. It would cost 1/4 of the price. And also you would be using 1/4 of the natural resources that you would be using when you're using a circular arch. So that is why these form-find structures work so well, because they follow the flow of the forces. And I'm going to talk specifically about shells. This is very relevant because, as I said, we've just gone through a storm. So I think a lot about extreme events like earthquakes and tornadoes and hurricanes. And it has historically been proven, there are lots of images like this, that shells actually, when a natural disaster or a man-made disaster occurs, that shells actually resist that, right? So we have images here of hurricanes, the bottom ones in the US. This is tsunami. This one is top left is earthquake, at the fire in San Francisco on the right-hand side. And so we were interested in finding out, why do these shell structures, so very thin structures, why do they behave so well? So shell structures, as we also saw on the intro slide, we find them in nature. So they are really thin, curved surfaces where one dimension, so that is the thickness, is much smaller than the other dimensions, like the span and the width. And so basically these shells, they basically take all their forces within their surface, right? Don't worry about the image that you see there, that is all the forces that they are taking, but they're very good at taking in-plane forces. And especially corrugated shells like the ones you see here and the ones that were on the intro slide, they're really optimized for impact loading. So these natural shells, as you know, who are their enemies? Well, it's the birds, right? The birds want to get to the weak animal that's inside, so they will either drop these shells or they will attack them with their beaks. And so, first of all, the surface is curved, and secondly, it's corrugated, so it has even more tiny curvatures in there. So we wanted to find out, why do shells behave so well under impact loading? And there's no better example, if you're interested in shells, at looking at the work of Felix Candela. This is the Church of the Miraculous Medal. It's in Mexico City, and it has resisted many earthquakes. I don't know if you know this, but Mexico City is subjected to many earthquakes, and this structure always performs well. No damage under earthquakes. Don't worry about the numbers here, but basically what we did is we modeled this shell in finite elements, and then we looked at what the eigenfrequency is. That is basically the frequency at which it tends to resonate. And for the shell, it's 3.09 hertz. This is quite high, and that is because it's a function of how stiff this thing is. So you see this formula here. Basically, you have at the top K, which is stiffness. So it has very high stiffness, and M is mass. It has very low mass. It means it's very thin. We know that. So it doesn't weigh a lot. And K refers to its stiffness. It's very stiff. And it is very stiff, not because, unlike the seawalls that I show you in the beginning, it's not because there's a lot of mass there. It is because this form is curved. And so if you get very high fundamental frequencies, the frequencies of the earthquake are much lower, and so they will not interact with each other. And that is why these shells, although they are very lightweight, they do not experience a lot of damage in earthquakes. And it is really because of their very, very high stiffness. And the high stiffness is achieved not because there's a lot of material, but it's achieved because they are so curved. And so we started looking at how can we, for example, an arch, how can we generate shapes for arches that are good for earthquake loading? So as I mentioned before, Robert Hooke already solved the riddle of what is a good shape for an arch under self-weight, and that is the blue shape that you see here on this drawing, right? That is the ideal shape for an arch under self-weight, totally based on Robert Hooke's statement. But what if we have earthquake loading? Now, earthquake loading is actually a horizontal load. So for that, we also have to introduce a horizontal load on this arch, and we end up with the green line. So the green line is really the ideal shape of an arch under self-weight and earthquake loading. And you see here again, top left image, you see the green line. That would be the ideal shape of an arch under self-weight and earthquake loading when the earthquake would be coming from the right-hand side. Of course, the earthquake comes from the right-hand side and shakes, so it also comes from the left-hand side. So we have the mirror image that line. So we now have the red line. And if we take those two lines and offset them, we can actually define the shape of an arch that is really good at taking earthquake loading. So I'm now looking at the image on the bottom left. That shape is the ideal shape for an arch under self-weight and earthquake loading. Now you might say, well, that's a really weird looking arch, you know, like there are circular arches or basket handle arches, or maybe kind of parabola looking arches, but this line is really weird. And I don't even know how you would make that. So I will come back to how we could make that, because as you know, most masonry arches are made out of bricks, right? Like very regular elements. So how could you make such an irregular shape out of bricks? And I'll come back to that. So we also checked that when you see bottom right, we checked, and indeed this system or this shape is really good at taking self-weight and earthquake loading. But that would be like a two-dimensional shape. We are interested more in covering spaces, right? And what you see here, top left, again, is that shape that is good in 2 dimensions to take self-weight and earthquake loading. We mirror image it, and now at B. C, instead of developing a 2D shape, we are interested in doing a 3D shape. So the second curve, we're now going to offset it with half a period of P upon 2. And we can then copy that shape a number of times and fit a NURB surface to it. I'm now looking at E. And so basically now we have a shell shape, right? A corrugated shell shape, which our hypothesis would normally behave very well under earthquake and gravity loading. Now, corrugated shells have already been built. What you see here on the left-hand side is a picture of Eladio Dieste's catenary shell, which has corrugations in it. It's from 1978. And on the right-hand side, you see a 3D printed model of our shell. So basically, they kind of look the same, but the difference is that the Eladio Dieste shell, the corrugations carry all the way through, whereas in our shell on the right-hand side, they're slightly offset. So we get here at the top of our form-fine shell, we get a different geometry than at the in the Eladio Dieste shell. And so we are interested in, okay, which shell behaves the best? So at the top, at the bottom right, you see a Dieste shell. And then all the other ones, FF1, FF2, all the way up to FF5, are 5 different parametric variations of the shell that we are proposing, because we can vary both the depth of the where it touches the ground, and we can also vary the periodicity. So if you look, for example, at FF5, that has a very large periodicity and quite a wide base. But if you look, for example, at FF2, that has a very small base and a very small periodicity. And what we did is we subjected these forms in a nonlinear pushover analysis to see under what loading these shells start cracking. So we are assuming that this is concrete, just like the Eladio Dieste shell. And basically what we see is that indeed we get 4 hinges, so 4 places where we get cracks occurring. So these shells are not going to fail because one crack occur. It's going to occur because in 4 places we get really cracked zones. And what you can already see from these images is that sometimes the cracks always occur at location A and E, which is at the base. But then sometimes an additional crack zone occurs at the crown, see, like for example for FF2. And for other examples, it occurs at B and D. Let me go to the next slide. Okay, so whether these cracks, so we see that, you know, the crack zones at C, they occur for the shells that have a very small width. So it occurs for FF2 and FF4. And the crack zones where we have crack zones B and D occur for the shells where we have a wide base. So basically, by doing the geometry, we can control where the cracks occur. And what we are seeing really is that cracks will occur at the places where we don't have double curvature. So at the top, remember I said the top is different from the LIDO-diastasis. We have zero curvature here, zero Gaussian curvature. And also here we have very low curvature. So that's where the crack zones will occur. And if we now compare the 6 different examples with the diastasis shell, which is an existing shell, as our example, we see that what you see here on the graph is the absolute peak ground acceleration. So that's the acceleration divided by the peak ground acceleration. And we see basically that shell FF3 is behaving the best, right? Shell FF3, especially, well, all the shells, first of all the shells behave better than the LIDO-diastasis shell. So that means that they will crack under a much higher acceleration. So that means that they can carry much higher earthquake loads than the LIDO-diastasis shell. And we see that especially shell FF3. So that is the shell with very, very small periodicity, right? Very tiny waves. And with a wide base, that one outperforms all the other shells. So that's really wonderful. We have now defined a way to define the shape for shell structures, large span structures that can resist both self-weight and gravity loading. And this is very beneficial, especially for areas with earthquake loading. And you see here a rendering of such a shell proposed in San Francisco, which is, you know, very seismic region. As I mentioned before, it's actually the reason why shells are not being built that much today is because of the materials involved, and that we've solved, right? If you do form finding, we don't have to use that many materials, but also the labor. And well, actually, the materials itself are not that much, but the materials to construct the formwork are very, very expensive. They can be up to 40% of the construction of the shell. And so we are now interested in finding a construction method that we can use so we don't actually have to build scaffolding or formwork to build these curved forms. Because as I mentioned before, that can cost up to 40% of the project. Because basically what happens is you first have to build a wooden scaffold and wooden formwork. So you basically build the shell first in wood, then you put your concrete or your masonry on top of it. And once that masonry or concrete shell is completed, then you take away the timber scaffolding. And so we are interested in, can we do that without the formwork? Is there a way that we can construct so that we do not have to support this system continuously? And we were inspired by this dome here in the background. Again, if you ever get to go to Italy, this one is in Florence. It's the Brunelleschi's dome. So Brunelleschi was a watchmaker, and there was a competition to cover what you see here in the background, to cover, this is a cathedral, to cover, this was already built, and they wanted to find a way to build this dome. And Brunelleschi proposed a method, and the rumor goes, and Brunelleschi kept this very secret, that this dome, the one that you see here in the back, was built without, or could be built without formwork or without scaffolding. And so this is a well-known secret, you know, people have written about it, but nobody has really proven how that would have been possible. And so, you know, I set out with a colleague and a student from the University of Bergamo to discover how can you build such a dome without supporting it during its construction. And what you see here are some drawings. This is by Antonio Zangalo the Younger. These are the masons that were working around that times the early Renaissance in Italy. And on that drawing here, you have some old Italian. It says hemispherical domes built without formwork in Florence. So basically what you see here on the drawing, you see part of a plan view on the left. What we see is that we have horizontal courses of bricks as well as vertical courses in bricks that spiral from the bottom to the top of the dome. On the right-hand side, we see a cross-section of the dome. So actually we see that the dome in Florence and many of these Renaissance domes are double-layered domes. There's an inner dome and then there's an outer dome. And basically, of course, as you can imagine, if you construct the inner dome completely, then you can use that as a scaffold to construct your outer dome, right? And they can be connected through these elements here, these yellow elements that you see sticking out. So what you see here on the right-hand side, this is a rendering of what such a dome could have looked like. We're now talking about the inner dome, right? And we see the spiraling pattern. Of course, what you see here on this dome is the dome that we investigated. Is not quite the dome that you see here in this drawing here, because this has spirals going only in one direction. We investigated because there's many Renaissance domes that have these spiraling patterns going in two directions. So that's the image that you see on the right-hand side, and that is what we investigate. So here is again a rendering of the dome of many Renaissance domes that have this spiraling pattern. And you know, people might think, oh, that's purely decorative because it's kind of beautiful. But actually, we have discovered that the spiraling pattern is key to have a construction method where you don't really need any additional supports to construct. And what is key here, and if you're interested in this, please contact me. We have just published a paper about this, which has gotten quite a lot of publicity because it's really kind of unrevealing a mystery, because people have not really known how this was possible. But what is key is what you see here on the left-hand side is such a dome under construction. Two things are important. One is that the bricks are always horizontal. We have horizontal layers that are completed. So it's not built in ladders, it's built layer per layer per layer. And the other thing is also these spiraling patterns. These bricks, we call them the herringbone bricks. They're sticking out. And basically what happens is that once the dome starts leaning inward, so as we are building it layer per layer, course per course, and we're going towards the top of the crown, these vertical sticking out bricks, which are stuck in the layer below, they are key. Because what happens is once you put the horizontal bricks between the vertical bricks, they would normally, if there is no friction between the horizontal bricks and the underlying bricks, they would just slide out, right? If it was like a Teflon surface between the two, these bricks would slide out. But because there is friction between the horizontal bricks and the layer below, and because these vertical herringbone bricks are slightly oriented towards the centroid, these dark gray bricks, they kind of jam into the vertical bricks and get stuck. And in that way, as you are building up your dome, you can construct the entire dome without any formwork whatsoever. And of course, I am interested in seeing, you know, like how can we use this old technique that Filippo Brunelleschi used to construct a number of Renaissance domes in Italy. How can we use that today to construct shell structures, right? Because if the formwork, if shell structures are very efficient, but they're not being built because, you know, you need to construct all that timber formwork, can we build forms that actually don't need formwork? And my idea is, you know, I haven't tried this, but this is my dream. Could we build them with, for example, drones, right? Like, could drones put bricks down? Or could we, for example, build them with robots? We were very fortunate to work together with the Create Lab at Princeton University and SOM, which is an engineering architectural consultancy in New York, to work on a small shell, glass brick shell, which you see here, which was completely constructed by robots. And as you can see on the left-hand side, the two robots are putting bricks in place, and there is absolutely no formwork whatsoever, right? So that was really the objective of can we find shapes, in this case shapes as well as a tessellation pattern of the bricks, so that the shell is stable under all phases of deployment, and we don't need any formwork or any props to prop it up during the construction. And if we can do that, we can save a lot of cost on the formwork, which is beneficial for the client, but it is also beneficial, of course, for the environment. And of course, this was a project with robots, but of course, if we can find shapes and tessellations in which this is possible, this could, of course, also be done by masons. All right, so I've been talking about shells, but in general, my research goal is to really harness the exceptional mechanical properties of slender surfaces. And I want to go back to my initial slide. You might remember this slide. This is the seawall in Brick in New Jersey. This was the response to all the damage that was done by Hurricane Sandy. The response of the community was, okay, let's build a big wall. And as I mentioned, I don't think that this is the solution. The design philosophy of pursuing strength through mass is, I think, not the solution for a number of reasons which I've mentioned. It prevents people from enjoying the beach. Animals cannot migrate between the beach and the water. It brings down real estate value. So I propose something else. My hypothesis is that we can use deployable flexible barriers that can be pressurized by air or water. And they can be strong and stiff enough and non-wave resistant to resist very large loading from, for example, storm surge events. And so this is not real. This is a rendering of my proposal for instead of building a massive seawall, which is permanent, I propose a lightweight pneumatic storm surge barrier, which you see here depicted in a corrugated form. This barrier would be stored underneath the boardwalk, and once the storm warming comes out, it would be deflated. It would be inflated. It could be inflated in a matter of a day, and this barrier would be strong enough and stiff enough and non-wave resonant enough so that it could actually keep out the storm surge loading. And once the storm is gone, this structure could be deflated, checked and then packed up again and stored beneath the boardwalk. So it would be an intervention that is very lightweight, deployable, so it's only there when it's needed, and it's a different kind of system. And also because this material, and I will talk about the material, it's vulcanized rubber, has a lifespan of about 25 years. This barrier could be every 25 years be redesigned with in mind the changing climate. So, and you might remember that picture that I showed you at the beginning of all these people on the beach. So this is now a map of where that is. This is Rockaway Peninsula near New York City. And so I'm proposing to work on barriers around here. It could, for example, that barrier could, for example, be positioned here. And what we see here is that we see here a cross-section of such a barrier, right? So on the left-hand side, you see the water. So there's three kinds of forces that such a barrier has to resist. Of course, the hydrostatic loading, that's just the water leaning into the pneu. We have hydrodynamic forces, that is the waves that are hitting it on and off and on and off. That's the light blue. And then the dark blue is, sorry, that's a hydrostatic. And then the gray is the wave break. We also, when the waves break on this barrier, they also exert very large forces. And so we are examining this barrier at the moment, and we are finding that both the very large deformations, because it deforms a lot, as well as the stresses that are in this balloon are actually very reasonable and can be carried by such membranes. So I hope that I've been able to show you that what I'm trying to do in my research is that I'm interested in studying how structural surfaces, so whether they are shell structures or membrane structures, like the storm surge barriers I've shown you at the end, how they interact with their environment. That we try to find new structural forms that are architectural form makers, and they are inspired by performance when we're using form finding methods. Art or history. We also have some projects where we look at plants and what shapes they take on, and whether we can upscale them for architectural or civil applications. And then also we develop all kinds of methods, graphical, analytical, numerical methods to generate these forms. So, well, I've come now to the end of my presentation. So if you're interested in my work, we have a website, formfindinglab.princeton.edu. We are present on Facebook. We have a great blog that you can follow, and we also have a really popular Instagram account that you can follow. Of course, I cannot do this work alone. I have a great crew of young, motivated undergraduate and graduate students, both architects and engineers, that work with me on these problems. And you see some of them sitting there. This is near a fire pit, but actually that fire pit is right in the middle. If you look at the right image, you see it as well. That's the fire pit. So one summer we worked on investigating whether we can use earth as a building material, and we constructed this rammed earth wall project. It was a fun project where we actually got to do some physical work and test all our numerical work and see whether actually in reality it holds up. It holds up. So basically that is the end of my presentation. I will maybe stop presenting, and I would be happy to answer any questions that you might have.
Thank you, ma'am. It was indeed a very informative session and very enlightening in many ways for, I think, everyone interested in shell structures. So I think we didn't want the presentation to end. We didn't know how an hour has passed. So that being said, I think we'll now
Thank you so much, ma'am.
We'll take a few questions. Those who have questions can use the raise your hand button, and once we call your name out, you can unmute yourself and ask the question. So if anyone has a question, please press the raise your hand button and we'll get to you. Questions?
So can I begin with the question?
Yes, definitely, sir.
So that people will take some time to get onto the
absorb
questions.
what is
yeah. Yeah, thank you, ma'am. That was really a great pleasure in watching the presentation and learning few things which we did not know, and so that is the value addition and knowledge addition to us. The question is like, first question is that about those corrugated arches that you have modified arches or with alternate corrugation at the bottom. What could be the solution for the formwork for that if it has to be built? So what can be the probable solution for building that kind of arch?
Yeah, so I think that's a really good question, because you know, we can develop all the shapes that we want, but if we cannot really construct them in an efficient way, then there is really not much point, right? All the material savings that we are making by making these arches or these shells in a specific way, it goes away if we have to use a lot of material to construct. So to answer your question specifically about the arches, and I think I didn't really talk about that. So one way is really, you know, irregular shapes are, I'm not going to say are not a problem anymore, but, you know, with all the digital fabrication methods, these are becoming less of a problem. And so I have a colleague here at Princeton University who is looking into 3D printing of concrete. And so, for example, if we could 3D print them, then, you know, then it doesn't, you know, as you know, the printer doesn't really care how many different letters it has to print, or if it has to cut irregular shapes. So 3D printing would be a possibility. But the other thing that we have not looked at is how, if because not everybody has a 3D concrete printer. I mean, I don't really have one. But so another thing that what would be interesting, and my students start looking at is how we can tessellate. So how can we arrange bricks on structural surface, whether it's an arch or a shell? How can we tessellate them in such a way that we can get this kind of behavior? But I have not done. I mean, I've not done the work on the 3D printing of the arches, or I've not done the work on the tessellation of the arches. But I think that would be the way to go forward, because of course bricks. I mean, bricks are fantastic, right? But they are always very standard size. I mean, that makes it wonderful to design with them because they always have the same size. But when you're going into these more irregular looking shapes, how do you match that brick, which is a very specific form, without wasting too much material? Because I think what masons do is they chop off bits, right, of the brick. But if we don't want to do that, we want to keep the brick all, like, what would be the most efficient way to either lay them in a pattern so that we can make these irregular shapes, or the other way would be to 3D print. But we're still far. I mean, I'm not saying we're far from 3D printing concrete, but yeah, it hasn't really come to the normal construction sites yet, right? So that's another, I don't know, 20 years or something before we're going to see that on construction sites.
Thank you.
Thank you, ma'am. Now we'll have a question from Professor Jairam, sir.
Yeah.
So you can unmute. Yes.
Yeah. Good morning, ma'am, and good evening to all the other participants from India. Actually, I would like to congratulate you, ma'am. Very nice presentation, well organized one. I need to understand two things from your presentation. Just can you elaborate what codes and softwares can predict the reduction of sound level passing through the shell roofing materials? This is number one. And the number two is what is the latest developments happening on plates and thin roofed members? Yeah, I will just post that one in the chat box so that others can also understand that.
Yeah.
Please.
So your first question was about what tools we use, right, to generate these forms, and what are now. So there's two things really that we are doing. One is we develop tools to generate forms, right? And in order to do that, well, we use theories like the one by Robert Hooke, but we implement them in digital tools, right? We don't make hanging chain models. So for that purpose, for the more design part, my students often use Rhino and then Grasshopper, and then they code within that. Sometimes we also use optimization techniques, so we develop our own optimization techniques. Sometimes we implement them in Rhino and Grasshopper, or sometimes we implement them in coding. Now, so the one is to find the shapes, right, which is probably the more exciting part, or the more design part, where you actually have control over what the thing is going to look like, because you can make many decisions in the form finding procedure. But the other part is, once you've got the form, you got to analyze it, right? You have to make sure, simulate the forces, simulate the real material, simulate the real support conditions, and make sure that your structure behaves the way you want it to behave, or you designed it to behave. So for that purpose, we use different methods. So sometimes we use finite element methods, like the pushover. Specifically, I think your question was for the earthquake analysis. We use a pushover analysis in a finite element package. Basically, that is an analysis where the program increases the horizontal force, right? Keeps increasing the horizontal force until we get failure of the shell or the arch. This is will fail with 4 cracked zones that you're getting. So that is one way. This method, we use it for concrete, for continuous surfaces, reinforced concrete. If you are analyzing masonry, which is different from concrete, because concrete is a continuous, like all the properties are everywhere the same. For masonry, it's different, because masonry is like a composite material. You have the bricks, and you have the mortar, and they both, they work together, but they behave differently. And so for masonry structures, you cannot really use finite element analysis. You cannot assume that the whole thing has kind of the same properties, because you will get crack lines between your mortar. So when we are analyzing masonry structures, so structures where you have brick or stones and for example, mortar, or it could be an epoxy glue, we use discrete element modeling. So basically in our model, we are modeling every single brick in every single mortar joint. So for example, for the Renaissance domes, that's what we did, right? Like, I don't really remember how many bricks there were in that model, but we modeled you cannot just model it as a finite element, like a continuous surface. You have to model every single brick in every single mortar joint. And in order to do that, you cannot use finite elements. You have to use discrete element modeling, which is kind of a brother or a sister to finite element, but it's slightly different. So those are the tools that we're using. For the form finding, we're usually using, methods like, for example, graphic statics or so, but we implement that in Grasshopper and Rhino often, or we use optimization methods that we implement in handwritten coding. For the analysis, we either use our own coding, or we use finite elements, or we use discrete element modeling.
Thank you, ma'am. I think we now have another question from Abhirami. You can unmute yourself and ask the question, Abhirami.
Yes, sir. So it was a great presentation, ma'am. So thank you for giving this presentation to us. So in your presentation, you have quoted some of the structures from Anthony Gaudi's work. So in your opinion, how do you think he managed to create such structures without any softwares or resources that we have right now? Because Sagrada Familia and all, they are building for like 130 years, like on and off, and
Yes.
it's still not yet completed. So in your opinion, what do you think about how he managed to build it?
Yeah. So Antonio Gaudi, so the works of Antonio Gaudi, so for example, you mentioned the Sagrada Familia, they're not all form-found shapes, right? So for example, the Sagrada Familia is not done with hanging chains. That is based on geometric figures. And so before, I think some of you might remember the time before computers, like when I actually started, we didn't really have computers. We did like projective geometry. We would draw things by hand. We would imagine what's the elevation, what's the section, and then I would draw it with China ink and then smudge it all, and then I have to like clean it up. So what did Antonio Gaudi? So Antonio Gaudi used hanging chain models. He used projective geometry, so he would draw what it would look like. So for the form find, he would do so for the force model, he would do hanging chain models. He would for the arches, for example, in the Collegio Teresianas, he would then cut them out of wood, turn it upside down. So he would do like full-scale form finding, right? So he would like cut it out of wood, have some pictures of that, turn it upside down, and then use that form that he had developed with a hanging chain, use that as formwork for his arches. So he also, for the Sagrada Familia, which is not forced model, but is based on geometric forms like spheres and hyperbolic paraboloids, he would use projective geometry. So he knew how to draw these things. We also have to bear in mind that, for example, the hanging chain model that he built for the Chapel Guel, like when I did the form finding for the Dutch Marine Museum, it took me a morning or a day to find that shape, right? And, once it was there, I could give it to the draftsperson, and, we could fit it into the analysis program. But Antonio Gaudi, to make that hanging chain model that you saw, it took a couple of years, right? And then once he was built, he couldn't really pass that on to the draftsperson and do structural analysis on it, right? Because it's not, it doesn't really work. He did put some measurement tools on it to get some measurements of some strains, like how much longer are the threads becoming. So one resource he had, which we don't really have that much today, is time. He had a lot of time to do that. I mean, people didn't build, if you go to an engineering or architectural engineering office today, people have many projects going on at the same time. He didn't really have like so many projects. That was normal at that time, right? So basically he used physical models or drawing. Then he passed away, and as you correctly said, the Sagrada Familia is not yet finished. And so then people started working with the drawings that he had left behind. And of course, as we move on into the 21st century, the tools, the masons that he was working with, we don't have masons with those skills. Well, maybe we have, but they're not so abundant anymore. So today we have different tools. We have digital tools, we have CNC machines. And so if you're interested in how people are now building his work, he didn't leave all the details of what this thing should look like. So there are actually people doing research in that. I particularly refer to the work of Mark Burry. He's in Australia. You can look up his work. So he was the architect on that project for a while. And he really brought that project from drawings on paper onto the digital world, geometry. We do the geometry on the computer, and we make the stones. We cut the stones not with the chisels anymore, but we do it with CNC machines, right? And so there has been a whole work of how do we take these ideas from Antonio Gaudí, of which he left drawings, but not to the fine detail how to make this. How do we take it from that stage to a completed stage? And there has been, and this really a fantastic kind of transition. Somebody, and Mark Burry was mostly responsible, and his collaborators were responsible for taking that work from old paper onto the computer and then using tools that we can use today for making these very complex looking shapes. It's very, very fascinating. And if you're interested in that, please look up the work of Mark Burry. He spent large part of his life doing this. That is very fascinating.
Thank you, Professor. I think we'll take another question. This is from Prarthana Roy. Prarthana Roy, you can ask your question. Prarthana?
Yes, good morning, ma'am. Yes, good morning, ma'am. I'm Prarthana. I'm from 5th year. So my question is, since you've talked a lot about shells and how they're constructed, so application-wise, apart from roofs, and you've even given some storm wall examples, what according to you, where else can we apply the technology and processes for shells and their building?
Yeah, I think that's a really good question, and that is something that I'm trying to promote, because traditionally shells, for example, I'm the co-chair of the working group on concrete roof shells. So it's very specific, right? In these shells, they were very popular, or they were widely built in the 60s and 70s. I mean, you see the work of Felix Candela, but there's other shell builders like Pierluigi Nervi or Heinz Isler. And so at some point they were architecturally very fashionable, so they were built a lot. Before that, they were built a lot for very utilitarian purposes, like hangars and warehouses. Like, for example, the thing you saw from Eladio Diez, it's a warehouse. It's not like some kind of beautiful restaurant or something, right? So traditionally, excuse me, shells have been used, or concrete shells have been used for large span to cover large span architectural programs, such as warehouses, hangars, churches, train stations, everything that needs a long span. So basically no intermediate supports, just a few supports, quite high, and a large span, right? And so traditionally that has been roofs. Also, they have been used from a utilitarian point of view. I'm thinking now for power plants, right? You see the hyperbolic parabolic power plants. That's also what they have been traditionally used for. And I think people think that that's maybe the only thing that they can be used for, right? But so shells, if you look at the mechanics of shells, like seashells or any kind of shells, they're really extraordinary, because when you apply a load to a shell, it will distribute its loading throughout its surface. And so when it fails somewhere, if you get a hole somewhere, the loads will redistribute throughout the surface somewhere else. This doesn't really happen with other structures. If you take out a column of a building, the building will collapse, right? I mean, hopefully not, but they're not so basically they're very indeterminate. They can spread their loads. They're quite good at taking impact loading. And so if you look at what are the properties that shells have, all these things, they use very little material, they're indeterminate, they're very resilient. We can think about what other applications rather than roofs. We've been using them forever for roofs. What else can we use them for? And so, yes, we can use them for storm surge barriers, for anything, I think, where we have extreme loading, very high loading. They would perform very well. I have worked with my students also. We always think, oh, shells, because we think about concrete shells, right? They have to be very stiff, right? Because we don't want the roof to deform too much. But I've started looking at elastic shells, so shells that can deform. Now, what kind of applications would we have for shells that can deform? We don't really want things to deform. But for example, I mentioned I was looking at shells in plants. So a lot of plants, although plants, you might think they don't really move, but some plants move. You think about the sunflower head moves, right? It tracks the sun. There are other plants that move as well to capture prey. If you think about the Venus flytrap, that are two little shells that are actually like this. Once they feel that there's a fly, it catches fly, right? So that is an elastic shell that deforms. Well, you might think, well, that's tiny scale. What uses that for humankind? But so I've had a National Science Foundation funded project to look at what plants use shells to do movements like the Venus flytrap, but we found many other ones. And then we upscale that for architectural purposes. And for what purpose then, right? And so the application that we were looking at is, can we use these shells for adaptive facades, right? So as you know, the facade is building facades is the filter between inside and outside. And so maybe we want to filter the light that comes in, the heat that comes in. So we don't always want our facade to be completely open or to be completely closed. Throughout the day, we might want to vary it. And traditionally, this would be through louvers or through curtains that you can open and close. But if you devise a system that kind of, in a very efficient way, with very little energy, opens and closes to kind of keep out the sun or the lighting as we want it, right? And so we've been looking at shells that are in the scale anything between 10 centimeters to a meter that can deform a lot. They are based on forms that we find in nature, and we've actually developed, you can go to my website and check it out. We've developed a device that you can put on the facade. It's basically a shell. It's a compliant shell, so a very flexible shell that you can use for an adaptive facade element. So my quest is really to kind of get shells out of the reinforced concrete roof, right? Because they have properties that are really very beneficial for other applications. And I'm mostly looking at architectural and civil scale applications. But if you look at the work that's being done at a much smaller scale, shells have many applications. For example, in drug delivery, how we deliver pills, or how it goes in your blood, or something like this. But of course, that's a very different scale. And I think as architects and civil engineers, we have, for any kind of system, we have different challenges than at these small scales, because we have to work with gravity, and we have to work with materials that can be outside, and that can be outside for a long time, preferably 50 to 100 years, right? So we are more limited in the materials that we can use, and we're also more limited, in our things have to resist very high wind loads or gravity loads or seismic loads, which, you don't really have at the smaller scale. But anyway, it's a good question. It's my quest, right? Like to see these systems are excellent. What can we use them for in the architectural and civil realm?
Thank you, ma'am. Okay, do we have any other questions? I'm looking for raised hands. If someone has a question, you could ask. Ma'am, before that, if I could ask a question of my own. It might sound a little naive, but while you were discussing the shells, the corrugated shells that you had worked on, and you were mentioning the earthquake pressure from the left or the right side, and that being the basis for the shape, what happens to the front and the back direction, the pressures when they're applied?
Yeah, no, actually, that's a really good question. So indeed, we looked at what happens if the earthquake falls is within the plane of the arch. If it's out of the plane of the arch, it would fall down. So you would need something else. If you're looking at an arch, you would need something else in the other direction. However, if you're looking at the shell shape itself, the longitudinal shell, where it's very long, if the forces are applied in the direction of the length of the shell, the length of the shell will take care of it. There's no problem there. It's really more in the shorter span. And there, of course, then we have that shape, right? But if you had the art by itself, like you had a freestanding art and you had earthquake not in the plane, but out of the plane, that would be a problem. You would need a three-dimensional other thing to do that.
Right. I think we have another question from Pratna. Pratna, do you have another question?
Yes, ma'am. Actually, it's more of a suggestion rather than a question. Since you mentioned you're researching on shells which can be deformed as well, I'd just like to say if we can consider them for say forms or float plates which can be changed as per context. Like I know, like since site can't be changed much, but if there is some context which changes as per time. So if we can, if these shells which can be deformed, like they can be altered as per context. Like I'm not sure how to put this out. So as with times as it changes.
Yeah. So there's two things. Of course, for example, a floor plate or let's say a bridge deck, we want that to be quite horizontal, right? Like we don't want to don't want to stand on a floor that's like this. Would make us uncomfortable. But indeed, so for example, I have seen a project. This was for a bridge where the shape of the bridge, and this was not a shell, it changes as the truck or as the whatever load goes over the floor plate. And so I have not thought about it, but it's an interesting concept that you can actually change the form. So it would be like an adaptive system, right, where it adapts its shape in function of the loading. It could be very interesting, and it has been done for conceptually. I've seen a conceptual project for a bridge, which I thought was very interesting, where the shape is changing as the is moving over it. It would be interesting to see whether you could do this for floor plates as well. Maybe not so much for like people walking on the floor. That seems like to me a little bit excessive to be changing your floor plate. But for example, maybe you have large loads on your floor plate, or you have a piano or something. Like how could you adjust the floor plate once in a while to adjust the loading? No, that's a very interesting idea. I have not explored that, but I think it's worth thinking about. Like how would that be done? Yeah, and for what applications? What would the loading be? But it's interesting.
Do we have any other questions? Because I haven't tried it out. Ma'am, if I could ask one more question. It's about the surge walls that you were talking about and how they will be taking the pressure. But how do you anchor such large units so that they don't move or they can bear the force?
Of course, you don't want these balloons, I'll call them now balloons, to be floating up, right? So they would have to be anchored. As I mentioned, they would be anchored in so they would be stored, they have to be stored. So what I'm imagining is you have the boardwalk, so basically the planks underneath that there would be a gutter, a big concrete gutter, in which they would be stored, and they would be clamped to that. So basically you can clamp the membrane, and this is actually a proven construction detail because I'm not the first one to kind of keep out water with an inflatable system. This has been done for dams, small dams, right? So much smaller scale, much smaller loading. And so there they have clamping details. So basically you can take the membrane, hold it back on itself, and then clamp it down onto a concrete foundation. And of course, as you rightly remark, the forces on that concrete gutter or the concrete foundation are very big, right? Because the balloon wants to lift up. So basically, the gutter is not just like a gutter. It's really a gutter with a foundation on it. It also has what we call skirt walls, so that the water doesn't go underneath, like erodes everything. So you have to make sure the water you don't get like a water flow underneath it. So it would have, we call it a caisson foundation. So quite a big concrete foundation underneath with skirt walls to make sure that the balloon doesn't lift up, to make sure that the water doesn't go under, and that the caisson itself provides enough counterweight for the balloon, which will be exerting quite large upward uplift forces, and that would happen through a clamp, and that clamp detail occurs maybe every foot or something. You have this membrane clamped down onto the foundation. But yeah, it has to be really kept down. The other thing is also, of course, we would have to think about piercing, right? Like if a debris comes into it, you don't want the membrane to be cut and to go down. So there's all kinds, you can have double membrane, like 2 layers of membranes, or you could have compartmentalization. So you could have different tubes with one large membrane over it. Yeah, but there are many practical considerations that would have to fulfill to guarantee safety and non-failure of this system.
Right. Thank you, ma'am. Do we have any other questions? I think everyone is, again, absorbing all the information. Yes, sir. Principal, sir, you have something?
No, there's one Padma Shri. Someone.
Yeah. Padma Shri, you could unmute yourself and ask the question. I'm not able to see you on my list, though. I'm sorry.
Good morning, ma'am.
Yes.
Good morning.
Good morning, sir. My question is, if given without the concrete as a shell material, can we use any other material like aluminum or Teflon? To what extent can we use any other material rather than concrete?
Yeah, so that's a really good question. So the wonderful thing about shells is that because of their form, I think I mainly emphasize that they're very stiff, right? So they if you design them in a specific way, they will be very stiff and they don't deform a lot. But the other wonderful thing is that because of their form, if designed well, if you use these form-finding methods, will follow the flow of the forces, actually your stresses are very low. And so also what you saw, I did not really point that out, but in the Felix Candela analysis that we did, we see that the stresses in the concrete are under the earthquake loading, with the self-weight on it. The stresses are actually very low and the material doesn't really break. So in general, these shells, because they have the right shape, take these forces, the stresses are very low. So that means that actually we do not need very high strength materials, right? Or you mentioned like if you think about Kevlar and stuff like that, that is for where you need really high strength. We don't actually need very high strength. That's why we can make it out of concrete, or why we can make it out of masonry. Wooden shells exist. Grit shells, because the examples probably that I've shown and that you're thinking about are continuous surfaces, but you can also make them into grits. So there's also grit shells. They're often made out of wood, made out of bamboo. All construction materials that are not necessarily very strong, but maybe that are very flexible or very durable. And so that's the wonderful thing about shells, that you actually don't need very strong, you don't need very specialized materials. So concrete, masonry, timber, bamboo, laminated timber, I've seen aluminum. The grit shell, I showed the Dutch Marine Museum. That's a steel grit shell, steel and glass. So all these materials are good. Of course, if you want your shells to deform, like for example, the adaptive facades that I'm talking about, right? Those materials, that's not concrete or steel. That is like composites, right?
Yes.
There are composites that can deform, because there you get very, like they will deform one way and another way. Of course, if you do that with concrete, or so if you make concrete move like this, it will crack, right? It doesn't work. So if you want flexibility, then of course you do need these more engineered materials. But otherwise, you can use, because the stresses are generally very low if you don't do these compliant shells. If you do shells that are rigid, you don't really want to deform them. You can use quite low or materials with that are not that strong, compared to the high-tech materials or the very strong strength materials that you were referring to. They are not necessary. Of course, you could make it like that, but it's not really necessary. And so, as I said, like I've also once done a grid fill out of reinforcement bars. Like you could use that reinforcement bars and the fabric, something. That could be a grid shell with a fabric roof on top of it. Anyway, I don't know if that answers your question.
Thank you, ma'am. Do you have another question? Ma'am, as a follow-up to this, the loading chain that you talked about, will be changing with respect to the material that you use, right? So you will not have the same curvature. So if it's a lighter material, there will be lesser curvature, I assume?
Yeah, correct. So I didn't really talk about that, but so basically depending on, you will get different shapes, right? And so it depends on two things. One is how elastic is it, right? If you think it's a rubber band, it will deform a lot. If it is a metal chain, it will not really, it will still take a good shape. So there are, if you think about that chain between two supports, whether you hang it and it's steel, it will take the same specific shape. If you hang it in rubber, it will take a different shape. So there are many parameters. So there are many shapes that are what we would call funicular shapes, right? These good shapes.
Right.
So that is really the choice of the designer, right? Whether you're going to use a very stiff chain or a very flexible chain. And of course, what you have to bear in mind, I didn't really explain that, but in the form finding process, we actually use fictitious materials. So we can actually choose the stiffness of our chain to get a much taller shape or a very shallow shape. I can change what we call the elastic stiffness, right? I make it more rubbery, or I make it very stiff. If I make it very stiff, it will not really deform. It will be like this. If I make it very rubbery, it will be like this. Now, all of these shapes are good funicular shapes between the 2 points, right? So any of this shape, I turn it upside down, I will get like an actual truss line. Now, the stiffness that you choose in your form finding process, whether I make it very rubbery or I make it very, very stiff, like for example, steel, that has got nothing to do with the form that you are eventually building. So if I refer back to the design example of the Dutch Marine Museum, where we had that grid, and then I said we used algorithms and we get this hanging chain, the properties that I put in that original mesh, to make it go like this, these are not the properties of the beams that are eventually used in the thing. I just put rubbery properties, so we get a shape of a dome that has kind of height that we wanted for that thing, and we use that shape, and then we assign steel beams with particular cross sections or whatever, and we analyze it. But for the form finding, I don't use those steel beams properties, because you can imagine if I put steel beams like this, it will not deform like this, right? So in the form finding process, we use fictitious material properties. So we use fictitious stiffness. We use more stiffness if we want to get it to hang, or we use a lower stiffness, so not very stiff, to get very hanging through shapes. If I don't want this kind of very large deformation, but I want more shapes that are more shallow, I will use more stiffer materials. These materials do not reflect the materials from which it will be built. It's just to get a good funicular shape, and I can get it with materials that are very stiff or materials that are less stiff, and that is just going to control how much it is hanging through.
Great. Thank you, ma'am. And I think we're done with the questions. Just a last question, ma'am. I can't help myself. Yeah. Principal sir, you have a question?
Yeah. Just.
Shashank sir?
I have a question. This is from the point of view of a teacher, in fact. Like all the architecture students, it is generally observed they are weak in this subject, structural design, and because it deals with mathematics, and they think that is more complicated, and so they become nervous also when they learn this subject. But it is inseparable part of architecture, structural design and structural system. So what is your advice, like as far as the developing the structural intuition, if I may say, or structural thinking? What students should look for? How should they develop structural intuition so that their structures or the forms they develop do not go against the laws of nature or something like that?
Yeah. So let me start by saying that architects are not the only ones who are nervous about this. Like if you talk about shells to engineers, they will say, well, no, let's not do that. You know, that's the old times. We don't do that anymore. And it's really because this is not taught in engineering schools. So let me maybe first reassure you, if you're feeling nervous, that's okay. Imagine how if you were an engineering student, you'd probably be like, oh my God, I haven't seen this at all. I don't know what she's talking about. So let's say shell theory was taught in the engineering curriculum up to a certain amount. Now, I still teach shells, and I reintroduced it in the curriculum. I think I might be one of the only places in the United States where this is being taught. So just to make you feel comfortable, if you feel nervous, even if you were an engineer, you would also feel nervous because people don't really learn the theory about this anymore. You know, we have finite elements, so engineers will maybe feel comfortable analyzing it in a finite element method because they have the tool, they can import it and look at it, but they would not really intuitively know how this thing is supposed to behave, right? Because they haven't taken any classes. But so actually I also teach, I teach a course form finding of structural surfaces, and I've taught architectural studios. I think the most important part, besides what are the forces and what is eigenfrequency and what are all these things, the most important part to, for example, generate these forms. If you look at how Antonio Gaudí did this, right? He did this with hanging chain models. And I'm not saying you have to build hanging chain models, but physical models are super, super useful to develop an intuition. And so in my course, Form Finding of Structural Surfaces, which is both taken by engineers and architects, and they both feel nervous about this course, so we have a computational part, right, where we generate shapes for shells and for membranes, but we also have a physical workshops. And I think the students actually like those the most, because I think in engineering and architectural education at the moment, there's a lot of emphasis on doing stuff on the computer, and not so much anymore on the drawing, sculpting, modeling by hand. What I have found both for engineering and architecture students, and even for, I also taught in a sculpting class, if we do these physical workshops, people get really engaged. And so I do a number of workshops, but the two that I can think of at the moment, one is for shells, we make a hanging plaster model. So we take a specific fabric, we load it with a liquid plaster, and we hang it. So basically, we do this the way that Heinz Isler would have done this. And by making physical models, you get an immediate sense of what is a good shape, what happens if I make an opening in the shell, how does this change, adapt? What happens if in my fabric I change the orientation of the fibers? You get a different shape. What happens if I introduce a rib? If I bring in like a thread, I get like a rib. And so this is so I do this workshop in like 50 minutes, right? Like the students are like, so I explain 5 minutes how to do it. I divide them into groups, and they have 10 minutes to do it, 10 minutes to draw, and 10 minutes conversation. And so in like a period of 50 minutes, they have made a physical model of glass, of course, not a beautiful architectural model, but we can see many things about the form, and that's really what we're interested in. And then sometimes what we do with these shell models, we actually do a competition where we're loading them, right, with books or something, and we see which ones perform the most, how much do they weigh, the shells, so we weigh them on the scale, and then we see how much loading. It's very, very exciting. So that's a very good intuitive way to learn about shells. The other workshop that I do is for membrane structures. So those are, again, they're basically textiles, right? Very thin membranes, they don't have bending stiffness, so they're not rigid. Again, we do this with lycra and dowels, and again, I explain 5 minutes what we do. I divide the students. They do it in 10 or 20 minutes. I say, okay, there's 4 archetypes. So you make this one, this one, this one, this one. They have 20 minutes to make it. We discuss it for 10 minutes, and bam, done. In 50 minutes, they have learned about the 4 archetypal types for membranes. They have learned about tension forces because the things are spinning out. They learn about curvature because, we put a ping pong ball, the ball stays, so it means there is no curvature there. So what I'm saying is, okay, I understand you're nervous about this kind of structures. Everybody is, engineers included. But there are, I think, very physical, you can do this on Grasshopper. There is a plugin called Kangaroo. You can make shell structures, like there's so many tools that you can do now. But to really get an understanding of how do the forces flow, what happens if I make a design change, do I get enough curvature, in which direction do I have to pre-stress more? These physical models are really, I think, key. And I think once you have done the physical models, you can use those, and you have a good shape, you can use those, and then I think start using the numerical tools, which are there anyway, right? Like Kangaroo, there's other tools like Form Finder for the membranes. They're very user-friendly, but I think the physical experience of how these things work, what are the forces, what can I do to get more curvature, the experience of the physical model is really, really important. And it's not scary because, or it's scary to you, but it will be scary to everybody because nobody's done that. Nobody's done that before. I mean, none of the students has done it before, right? And it's very exciting also to get, in a very short time span, like get a great shape for a shell, great shape for a membrane. Yeah, it's very, very rewarding, I think. So anyway, that would be my advice, to make physical models. They give you a lot of insight in the behavior and in the shapes that are possible.
Right.
Thank you.
Thank you, ma'am. I think it's a beautiful way to now wrap up this webinar. I think we've had an extremely informative and inspiring session. And I think we'll be going back with a lot of information, and most probably we'll explore more about shell structures in the near future. So thanks a lot, ma'am, for this session. I'd like to now call upon Professor Justin to give us the vote of thanks.
Am I audible then?
Yeah.
Yeah. Oh, thank you, ma'am. So it was a very wonderful session in this evening for us. So completely engaging our minds, and it was almost like for the past 2 hours we are completely drained, engaged into this shells, because it was, as we all were thinking, and as it always we felt like it was a dry subject, but it was so interesting for the past 2 hours for us. It is a genuine comment on that. So I think that was a wonderful session. Thanks for your energy levels for at least past 2 hours. So that is the best part I could have observed, as a desk teacher. I think you have taken us to a time travel kind of, disclosing the Brunelleschi's domes to the latest ones, the dynamic facades, and even the dynamic floor plates kind of. So much of information. There are lots of takeaways in this evening for us. So thanks for enlightening us on all those things. I think this one good learning that I personally had is though I was teaching here for quite some time, mostly we will be talking only about the roofs of the shell structures. We have never even thought of the vertical shells, and supposedly with so much of horizontal loads when you are talking about the storm surge walls kind of. And the best part again is we still were thinking about only solid shells, whereas today I just learned that it can be a flexible shell also, still taking the load and other stuff. So I think genuinely speaking, this is the longest session that any architect would have listened to from a civil engineer, because it always happens because most of the civil engineers get into the subjective kind of teaching, where we always take into the subjective kind of teaching mode. So I think that was a wonderful session with you here. I think there are lots of takeaways, right, from the basics of masonry to even the latest robotic construction and the latest software that is used here. So much of knowledge has been given to us. Thanks for Compounding Lab and yourself, ma'am, Professor Sigrid. We are extremely privileged to have you here, and we would even love to have you here in our college whenever you are free and whenever time permits that. Because you had said that you loved India and you have spent so much of time in your young days here. I think you can even still try out after all this COVID season is gone. Try coming here. We definitely love to have you. Because this is definitely an eye-opening session for all of us. And now, since you have given the tip of learning by experiments, learning by physical models, that was one great thing that we have to learn today. That because we always found it so tiring to engage our students, architecture students, into the civil engineering subject. Though we can't avoid that, it always happens to us like just one more subject which we'll have to just pass and clear this for taking a degree. So I think from today onwards, the students will definitely have an interest developed towards that. Thanks for this wonderful session, and I think it went on so nice. And thanks for the organizers, and thanks for this wonderful evening to us. And thank you. Thanks.
Thank you.
Thank you. Thank you.
Thank you all. It was
Sparing your time.
indeed a wonderful session, and I'm pretty sure all of us have a lot to take back home and research. I think we'll all be engaged in a lot of research regarding shell structures here onwards.